Welcome everyone. My name is Abel Markó and I'm a PhD student at ETH Budapest, and I'm going to present a research investigating the heterogeneities of sedimentary aquifers and their influence on the reinjection efficiency. So why is it important to deal with reinjection? Because this makes thermowater utilization not only renewable but sustainable. If you produce water and the produced water exceeds the natural supply, you will cause a pressure drop and the water level decline, and you simply empty your pool. This can be mitigated by reinjection. So after you used the energy content of the water, you inject back the cold water into the aquifer. Unfortunately, it's not always easy to reinject into porous aquifers, and there's plenty of potential issues associated with this. And we often experience that we are able to produce water, but we are not able to reinject with the same rate. One aspect which should be investigated is the heterogeneity of the fluvial deltaic porous reservoirs, which makes it hard to find the best location to reinject and to place the optimal doublet. So the distribution of the sandstone bodies, like the mouse bars or the distributary channels, provide sandstone bodies with significant extension, while the interdisciplinary base and the pro-delta environments result in rather clay sediments. So this gives the motivation of my study, since this mapping can help boosting reinjection efficiency and also the reinjection in general, which is unfortunately lacking in my study area, Southeast Hungary, and in general in Hungary. Here, in this case, the porous reservoir is the Pannonian fluvial and deltaic deposit, and my goal is to characterize this reservoir in sand body scale to map the extension of the sand bodies, and in general to determine the influence on the reservoir heterogeneity on the reinjection efficiency. So to this end, I used the 3D seismic block measured within the area and interpreted 10 horizons. Then I used, among others, seismic attributes, the root mean square amplitude as indicator of the change in the lithology. That way, the regions with high amplitude were identified as sand-prone architecture elements, as you can see in the workflow. And I also correlated these outcomes with well logs. And after that, I digitalized the polygons on the different horizons. Here you can see the progradation of the slope and the delta on the root mean square amplitude maps. Here the purple color would be the clay, while the red and yellow color and the green color would be the sandy area. So you can see that the slope is prograding and the delta units are formed with red and green colors. The second approach was the spectral decomposition. So I generated frequency maps along interpreted key horizons, and I also generated frequency decomposition color blends in pool blocks. And on both, I digitalized geobodies, also using the adaptive geobodies tool of the geotech software. So here you can see frequency decomposition color blend maps and root mean square amplitude maps on 2 key horizons or along 2 key horizons. And you can see that these maps highlight the same architectural elements, which were identified as sandy units. And I also mapped these sandstone boundaries, so I digitalized on the root mean square amplitude maps on the top, and also used the adaptive geobodies tool to digitalize these reservoir sandstone bodies as volumes. So we can see that the methods produce similar results. So the adaptive geobodies tool corresponds to the results of the manual seismic interpretation. The third method was the numerical simulation of theoretical cases. So we generated geological models alternating silt and sand and clay, and we produced a porosity distribution ranging 10% net to gross until 90% net to gross ratio. And we placed 2 wells, one production and one reinjection wells in these units. One of the results, one example, was the influence of the net to gross ratio on the operational efficiency. You can see on the figure, the top, the blue curve shows the additive pressure at the injection well when the production well is disabled, while the orange shows the decrease of pressure at the production well when the injection well is disabled. So it means that with low net to gross, high excess pressure is caused by the injection well, and similarly, the production causes a stronger decrease in pressure when the net to gross is low. And the first approach, which is in progress, would be the numerical simulation for a real case study, namely by using the mapped sandstones as input geometries with different scenarios. So the first scenario would be the doublet, when it's placed into a sandstone unit with limited extension. Second one is the doublet placed into different sandstone unit with significant extension. And the third one is the doublet when it's placed into the same sandstone unit with significant extension. And the indicator could be the pressure difference between the production and the injection well, and also the pressure at the injection and production point itself. So to conclude, these approaches can be used to propose optimal doublet locations or the location of field of doublets. This will help to decrease the pump energy losses, so it contributes to the efficient use of thermal water. And we can also say that spectral decomposition as well as the adaptive geobodies too can be powerful instruments to reveal the heterogeneities of a silicic-elastic aquifer. And at the end, numerical modeling can estimate the impact of the heterogeneities on the reinjection efficiency. So with this, thank you for your kind attention.